Today we are going to study about Boolean Algebra. This is week 3. Now, I hope you can see my second screen, all of you. If there is any difficulty, let me know. Boolean algebra is an algebra for logic variables and expressing logic variables as different functions and expressions. We have like operations that could be done. Addition, subtraction could be done, and we have some properties, we have special laws using Boolean algebra to manipulate these logic variables. Okay, so in here you see the structure is closed under plus or dot, meaning the set, like considering as a set, if X is in group B or belonging to group B and Y belongs to group B, then X plus Y also belongs to group B. Now, if X belongs to group B and Y belongs to group B, X dot Y also belongs to group B. Now, there is something called identity, rule of identity, and we have identity for multiplication and addition. Okay, so X plus 0, anything that is added to 0, it ends up in the same number, right? So also in logic variables, when you consider logic variables, if you have a variable here, when you add it to 0, the same variable results. So additive identity is 0. Multiplicative identity, when you see, it's 1 because any variable multiplied by 1 is the same variable, right? So x dot 1 or 1 dot x is same x. So multiplicative identity is 1. Next, the commutative property is valid in Boolean algebra. X plus y equals y plus x, or x dot y equals y dot x. So this is a commutative property in mathematics, also for Boolean algebra with respect to logic variables. Next is the structure is associative, means x plus y plus z equals x plus y plus z. Similarly, x dot y dot z is equal to x dot y dot z. The operators are distributive. The operators are basically multiplication and addition. X dot y plus z equals x dot y plus x dot z. Okay. Now we say a multiplication is distributive over addition. So multiplication is distributive over addition. Now one more law that is not in mathematics is there in Boolean algebra. X plus y dot z. In mathematics, we don't write it as x plus y dot x plus z, right? But in here, we can write it x plus y dot x plus z. In the place of x, y, z, you should imagine zeros and ones, okay? You should assume zeros and ones because all these variables are logic variables. Next is the structure is associative, distributive we have seen. Next is we are seeing about for every element x which belongs to set B or group B, there is an element x complement or x bar we call it, or x prime, is also belongs to the same set or group B. So x bar is called complement of x. So x plus x bar, when you do, it is 1. X dot x bar is 0. So if imagine x is a 1, x bar is going to be a 0. 1 plus 0 is 1. Now imagine this to be a 0 and complement is 1, right? So 0 plus 1 is 1. So when you add the complement and the original variable, you're always going to end in 1 as the answer. Next, similarly, when you have a multiplication, x dot x bar, when you have, it is going to be a 0. Like if x is 0, when you multiply with 1, it is going to be a 0. And when x is a 1, x bar is going to be a 0. And therefore, in this multiplication, at least one variable is 0. So the answer is 0. Now, in here you see there are at least two elements in the set x comma y in set B such that x is not equal to y. If that is the case, you have something like this. Set B is having two elements 0 and 1, and we have two operations, addition and multiplication. So x and y, we are giving the names for these variables as x and y. These names could be a and b also, whatever like is comfortable, and it is all dependent on the author. In here we have the names for these variables 0 and 1 as x and y. X plus y is like the operation, the variables could be 0 0 0 1 1 0 1 1. So when you have x plus y, this is the output of a logic OR gate, right? 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is 1. Now, if you want to give the truth table, this kind of structure is called truth table, right? So x, y here, x dot y, 0, these are the four combinations possible with two variables, 0, 0, 0, 1, 1, 0, 1, 1. X dot y is, wherever there is 0, the output is going to be 0 only, like the result is going to be 0. So 0 and 1 dot 1 is 1, okay? Now, complement of 1 is 0 and complement of 0 is 1. That is just inverted. Now, if you have variables x, y, and z, okay, x, y, z are here and many operations are possible. Like we have an expression like x plus y plus z, and we want to prove that it is same as x plus y plus z, okay? To prove that, prove the commutative associative property x plus y plus z equals x plus y plus z, we have made some more extra columns and make the process simple, okay? Now, plus whenever you have, it is logic addition, and logic addition, and it is from an OR gate. Imagine that it is from an OR gate. The output is from an OR gate. Means 1 plus 1, you should not say it is 1 0, but it is 1. Okay, from a logic OR gate, you get only one output, right? If you send 1 and 1 into the inputs of an OR gate, you get 1 as the output. That is, there is only one output line that gives 1. So that is the way you should get the output of this truth table, okay? So now to prove this law, associative law, you see 0 plus, like here I have got y plus z, and here I have x plus y, and then I'm going to add x to it here, and I'm going to add z to this here. So now see, y plus z, y and z, 0, 0, 0, 0, 0, 1, 1, 1, 0, 1, 1, 1, 1. From where is it? It's from the OR gate, from here. This is from the OR gate. Next is 0, 0, 0, 0, 1, 1, 1, 0, 1, 1, 1, 1, right? So I got this column. Next, I'm going to get this column, x plus y. So I consider these two columns, and here x plus y 0 0 0 0 0 0 0 1 1 0 1 1 1 0 1 1 0 1 1 1 1 1 1 1. Fine. Here. Next, when I add x to y plus z, I consider this column and this column. 0 plus 0 is 0. 0 plus 1, 0 plus 1 is 1. 0 plus 1, 1. 0 plus 1, 1. 1 plus 0, 1. 1 plus 1, 1. 1 plus 1, 1. 1 plus 1, 1. I've got the output of the left hand side, x plus y plus z. When I go for adding z to this, again, I consider this column, I consider this column and this column. So 0 plus 0, 0. 0 plus 1, 1. 1 plus 0, 1. 1 plus 1, 1. So wherever you find a 1 in any of the columns that are going to, sorry, in here, plus in here, in any of the columns, any of the rows in here, if there is a 1, the output is going to be a 1. Okay, so 1 here, so all these outputs are 1. So now compare this column and this column, they are the same. So we call it as, we prove that x plus y plus z is x plus y plus z. Okay. The commutative property is what? Commutative property is a plus b is b plus a, or a dot b equals b dot a. Okay, they are one and the same. We have proved it. Now, distributive property, we have two of them. X dot, yeah, we have x dot y plus z equals x dot y plus x dot z. So multiplication is distributive over addition. Okay. Now we can do it with I shall take you to my notebook where I want to show you the distribute. Yeah, you can see it for now, and I shall from the beginning I'll take it and revise you. Okay. So here again, x, y, z, all of the possible combinations we have got it here, like from 0, 0, 0 to 1, 1, 1. Now, for getting x, that is the left hand side, x dot y plus z, I need one extra column. If I have y plus z as one separate column, I have to just multiply it with x. So it becomes easy, right? So y plus z, y and y column and z column you take. Wherever you find one in, like maybe in x column or in y column or z column, doesn't matter, the output is going to be a 1. If both y and z are 0, the output is going to be 0. Okay, 0, 0, 0 and 0, 0, 0. All other places it's 1. Now when you multiply it with x, consider this column and this column, do the multiplication. Whenever you find a 0, the output is straight 0. Okay. Now here x is 1 in here, but if y plus z is 0, then the output is 0. It's 0 here only, so 0 here, but here 1 1 1 1 1 1, so the output is a 1. Now here, to prove the left hand side is equal to the right hand side, the right hand side is x dot y plus x dot z. So x dot y alone is here, x dot z alone is here. So x and y columns I consider. If I have 0 in x or y column, the output is 0. Otherwise, it's going to be a 1. So in here you see x column is 0. So up to 4 of these 0. And y column, you see y column is 0 here. So this is also a 0. Now x dot y both are 1 and 1. So the output is a 1. I hope I'm making sense. You're able to follow it. For x dot z, consider x column and z column, and wherever there is 0, like in any of these columns, your output is going to be a 0. Here you see x dot z, look for x is 1, z is 1, so x dot z is 1. In here, x is 1, z is 0, this is 0. X and z both are 1, output is 1. Now we are going to add these columns. Up to here, both entries are 0, so the output is 0. Here, there is at least a 1, 1 on one of the inputs, so the output is a 1. Now when you compare this column with this column, they are one and the same. So we say that x dot y plus z is x dot y plus x dot z. And I said there is a special law which is not there in mathematics, right? X plus y dot z, right? X plus y dot z is x plus y dot x plus z. So again, we have these columns and you have them same. Okay, after doing all the manipulations, it's the same. So we accept that here, x plus y and x plus z. Here you see they are one and the same. So we say x plus y dot z is x plus y dot x plus z. Now x plus x is x and x dot x is x. So if the same variable is added, like 0 plus 0 is 0, 1 plus 1 is 1, right? So if you have the same variable repeated with the addition as the operator in between, we end up in only one variable like this. Similarly, when two variables, same variables are multiplied, you get the same variable. Like 0 dot 0 is 0, 1 dot 1 is 1.
Excuse me, ma'am.
Yes.
If we take 1 plus 1, won't we get 1, 0?
Look here, proof for x plus x as x is here. He has just complicated it with the next bar, which is coming up next. Yeah, simple proof is like what I said. 0 plus 0 is 0. So it is like 0 is x. So output is 0 also. So that is again x. 1 plus 1 is 1. So therefore 1 is x. So the output 1 is also x. Similarly, x dot x is x. So consider 0 and 0 for both x and 1 and 1 for both x. That is the proof. Okay. This kind of expanding them with complement, let's not do it. We'll go for further other rules and then we'll come for this. Okay, here you see, here again he has used complementing for like proving simple thing. So I wouldn't go for it. What I would say is x plus 1. Okay, x plus 0, if you have, it is additive identity, so x will result. But if you add 1 to x, like imagine one of the inputs of the OR gate is a 1, the output is going to be 1 irrespective of the value of x, right? So therefore x plus 1 is 1. Consider x to be 0. Okay, 0 plus 1 is 1, right? Consider x to be 1. 1 plus 1 is also 1, right? The output of an OR gate. Similarly here, x dot 0. If there is 0 in any of the inputs of the AND gate, the output is going to be 0. So irrespective of the value of x, you're going to get only 0 at the output. When you double complement a value, when you double complement a value, a logic variable, you're going to get the original variable. For example, 0 double complement. If you do, zero's 1 complement is 1. If you complement it again, 1's complement, it's going to be 0. Right? So the same variable results. Now, when you add the complement of a variable to the original variable, when you add it, you're going to end up in 1 as the answer always, because if this is 0, you're adding 1 to it, it's 1. If it is 1 plus 0, if you make the complement of 1 would be 0, and the output is 1, 1 all the time. So x plus x complement, x plus x bar is 1. When you look at x dot x bar, it is always going to be 0, because somehow or the other, there is going to be 0 in multiplication. These are special laws, x plus x dot y. X plus x dot y is x. X dot x plus y is also equal to x. So the same variable is like in this part of the expression, and even this is called an expression. X dot y could be called as an expression. X plus y alone could be called an expression, and the whole of it is also an expression. So now x plus x dot y is x. X dot x plus y is also equal to x. Now for proving it, we apply a distributive property. So x plus x dot y is x plus x dot x plus y, right? So x plus x is 1, and okay, again, this for the special laws, anyways, I cannot escape without going on a sheet of paper to explain you, okay? So let us do this on a sheet of paper. And here, x plus x bar dot y, x plus x bar dot y is x plus y, and x bar dot x plus y is x bar plus y. Again, by applying distributive property, we will be able, and taking the common terms out, we can get the answers for these two. Okay, now Demorgan's law. Okay, till this slide, we will do it on a sheet of paper and come back. Okay, now give me a few seconds to change over. Sure, I'll zoom a bit. Just let me try. Maybe I think I should write it big. Oh, okay. I got it. Yeah, is that clear now? See, I can divide the rules of Boolean algebra into categories like this. First is rules of addition, rules of multiplication, rules of multiplication. Third is we can have it as like identity rules will go into these. We can have commutative property, associative property, distributive property. Hope my session is recorded. Do you see it recorded? Special laws. Now you see the first one, rules of addition. Okay, I'll go by rules of addition. Rules of addition is like this. Instead of x, let me use a because I'm comfortable with it. Okay, so a plus 0, a plus 1, a plus a bar, a plus a. Now, for getting the output for a plus 0, what you do is consider OR gate, give a here and the other input is 0. Okay, one input is a, the other input is 0. Now consider a to be a 0 first. Consider a to be 0. 0 plus 0 is going to be what? 0, right? Now if a becomes a 1 but still The other input is a 0. 1 plus 0 is what? 1. So the output is all the time following A, right? If A is a 0, output is a 0. If A is a 1, output is a 1. So we can write A plus 0 as A. My dear students, I wouldn't be able to access your chat window. Yeah, I have your chat window, no problem. If you want, you can stop me by opening your mic and talking to me. Okay. Next is A plus 1. A is one input, the other input is a 1. Again, send it through an OR gate, A, 1. So now, if A is a 0, if A is a 0, 0 plus 1 is what? A 1. If A is a 1, if A is a 1, 1 plus 1 is a 1. So the output is not following A here, but it is all the time 1. This is going. Okay, so A plus 1 is always 1. So we can write A plus 1 is always, A plus 1 is always 1. It doesn't follow A, but this one is always going to go to the output. Now, next is A plus A complement or A plus A bar, right? So here A and the other input is going to be the complement. So A here and A complement or A bar here. If A is a 0, if A is a 0, A complement is always going to be like, if A is a 0, A complement is going to be a 1. So 0 plus 1 is what? 0 plus 1 is 1. Now if A is a 1, if A is a 1, A complement is going to be a 0. So 1 plus 0 is also 1. All the time the output is a 1. So it is A plus A complement is a 1. There is a 1 somehow or the other in the inputs of the OR gate. Now A and A, A and A and A here, A here. So if now I have A to be 0, this other input is also a 0, the output is a 0. If I have a 1 here, other input is also a 1, the output is 1. All the times it's following A, right? So A plus A, I would say it is. Now to revise, A plus 0 is A plus 1 is 1, A plus A complement is 1, A plus A is A. In this, A plus 0, it's additive identity. 0 is additive identity. When I add 0 to any variable, I get the same variable. So this is rule of identity. Additive identity. Now, if you want, you can quickly take this. As you saw the presentation, it's not properly categorized into these formats. So if you would like to, you can quickly note it. Or it's going to be there in the video, right? So we'll go further. So whenever you have rules of addition, you should assume that the variables are sent through logic or gate. Rules of multiplication, the variables are sent through AND gate. For commutative property, associative property, distributive property, you may either send through AND gate or OR gate, and special laws, the ones that we saw last, we are going to prove them. Now let me go to rules of multiplication. Again, 4 of them. Rules of multiplication. So in that, one is A dot 0, A dot 1, A dot A complement A dot A. What I'm going to do, I'm going to send the variables through AND gate. Now, here I have A, the other input is 0. I don't have to explain too much about it because 0, any of the inputs of the AND gate in multiplication will produce a 0 only. So A dot 0 is 0. Now A dot 1, A and 1 here, A dot 1, if A is a 0, if A is a 0, the output is a 0. If A is a 1, the output is 1. The output is all the time following A. So we say that A dot 1 is A, which is multiplicative identity. We can say this is rule of identity for multiplication. Yeah. Now, A dot A complement A and A complement. This also I don't have to explain too much because if A is 0, output is a 0. If A is a 1, here you have A complement, and therefore we can say that is also going to be a 0. So A dot A complement is going to be a 0. Next is A dot A. A dot A, 0 dot 0 is a 0, 1 dot 1 is a 1. All the time it's following A. So we say A dot A is A. See, this is same as sending the inputs through a shorted AND gate, okay? Sending the input through a shorted AND gate means what? I can short the inputs like this. This input and this input are short circuited and I apply A here, I get a A. Sure. This also, I can say this is same as sending it through a shorted OR gate. OR gate, we like have a curved line at the input. For a AND gate, that becomes a straight line, and try to draw the symbols yourself and get practiced used to, okay? So I give here A, variable A, and at the output I get A. So it's same as sending the same A through two different inputs. I can either short circuit or I can send it through two inputs. We are here. Now, what is the third one? The third one is rules commutative property, right? The third one is commutative property. Commutative property is A plus B equals B plus A and A dot B equals B dot A, okay? This is second one. This is third one. Commutative property, A plus B equals B plus A dot B equals B dot A. So just see, when I send A and B through the OR gate, this input could be A, this input could be B. If I interchange them, it's like nothing is going to cause a problem for the output. It is going to be the same, right? A plus B, if I send like this, it is same as sending B here and A here. So if I have A, B, A plus B, B plus A, through a truth table, if I want to justify or prove 0, 1, 0, 1, 1, 4 combinations possible with 2 inputs, because 2 power n combinations possible, right? Combinations. So 2 inputs I have. So 2 power 4, 2 power 2, 4 combinations with 2 inputs, right? The input combinations are 4. Now 0 plus 0 is 0. And this way, if I do also it's 0. 0 plus 1 is a 1. 1 plus 0 is a 1. 1 plus 0 is a 1. 0 plus 1 is a 1. 1 plus 1 is 1. 1. The other way also is the same. So this is the proof for A plus B. Even you can prove the same here. A dot B and B dot A. A dot B is 0 and B dot A is also 0. 0 here, 0 here. So 0, 0, 0, 0. Only in here you have 1, 1, 1. So A dot B and B dot A are having the same outputs in the truth table. So we have proved it. Similarly, B and A plus B and B plus A have the same values in the truth table. So we prove that commutative property holds good in Boolean algebra. Hope no questions. Associative property. In associative property, we have A plus B plus C equals A plus B plus C. A dot B dot C equals A dot B dot C. Remember the truth table we had? We can have a truth table here also. We can make it ourselves. A, B, C are the inputs, right? So here, left hand side of this rule is A plus B plus C. So for that, we need to have a column B plus C, and then we can go by A plus B plus C. Okay, we can split it into easy columns, easier chunks. Okay, so now see combinations possible with 3 inputs, right? 3 inputs, 2 power 3, how many combinations? 8 combinations are possible at the input. What are the 8 combinations? From 0, 0, 0 to 1, 1, 1, right? 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Now B plus C alone, just simple. Wherever you have a 1, those are going to be 1. If you don't have a 1, both are 0. This is going to be 0. This is going to be 0. Otherwise, there is 1, and somehow in one of the columns there is a 1. So, okay, that's it. Now, you're going to add a column to this. So, a column, you see, 0. This column is also 0. So, this is 0. You look for such an option anywhere else in here. Nothing, nowhere. Like here it is all 1. So, you can fully write a 1 here. Here you find a 0. See if this column is a 0. No. So, this is a 1. So, otherwise, all are zeros. Oh my goodness. 1 second. Yeah, no phone call should come. No alarm should ring. Then it'll work fine. Next is, see, I'm in the same place. Okay. So now 1 and 1 in all the other rows, it's 1. So the output is 1. Okay. Next, for the right hand side, I have a plus b dot plus c, right? So a plus b as one column, and then the final, this one, a plus b plus c, right? A plus b plus c. Right? Now a plus b, look in here, these two, is there any, like all are zeros, so the first two results are going to be zeros, and here in all of these, there is one somehow or the other, so the output is a 1. Next, a plus b, this plus c, so c is here, so only for the first row both are zeros, so output is a 0. In here there is a 0, but I have a 1 here, so the output is a 1, right? And thereon somehow, like all of these are 1, so I can just fill ones here. So I look at this column and this column, they are the same, so I have proved that a plus b plus c is a plus b plus c. The same idea is for a dot b dot c is a dot b dot c. Okay, I'm not going to like do the truth table proof for a dot b dot c is a dot b dot c. Okay, you're going to do it. Now, next property is distributive property and special laws, right? Distributive property, we'll see. Distributive property is a dot b plus c equals a dot b plus a dot c. Okay, this is valid, right? The next is a plus b dot c equals a plus b dot a plus c. This is only different from mathematics. All other laws are valid up to this point in mathematics also. Okay. Now a dot b plus c is a dot b plus a dot c. Again, let's make truth table. A, b, c. 8 combinations, as I said for the previous case. So 0, 0, 0, which is the most significant bit and the least significant bit in here. Have considered A to be the most significant bit, C to be the least significant bit. And as I was saying you before, these could change in position. I could even write it as CBA, doesn't matter. Okay. So 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Let me keep the participants list also at the side. Now, for proving the first left-hand side, for proving the left-hand side, for getting the outputs of the left-hand side, I need a column for b plus c. So let me make a column for b plus c, and then the left-hand side expression a dot b plus c, and here on the right-hand side I have a dot b, I have a dot c, and then I don't need to. Okay, so a dot b plus A dot C. I can make it into a nice truth table. How cool is teaching from your own desk? Hope it's clear, guys. All right. Now you see B plus C. You look for 1. There is 1 here. 1, 1. There are both zeros. 1, 1, 1. So you have the answer for B plus C. Dot it with A column. So if there is a 0 in dot, like for the inputs, the output is a 0, right? So 0, 0, 0, 0. 4 zeros, so zeros. Next 1, here you have a 0. So because of that, it is a 0. But in these 3, it's all both 1. So 1. Finished? Next you see A dot B. A is a 0. So 1, 2, 3, 4 zeros. And from here only you should start looking. Here there are zeros. So 0, 0 also. But in here there are all ones. So ones. Next A dot C. A is 0 in up to 4 rows. So 0, 0, 0, 0. And here there are 4 ones. Now you look for C if there is a 0 or 1. This is a 0, so this is a 0. This is a 0, so this is a 0. But in here, both are 1s, so 1 and 1. Finished? Now, these two columns should be added, okay? So, you see 1s here only in the last 3 entries. So, 1s, they're all zeros. Now, look at, yeah, do it with me because you will have practice. That would be my strong suggestion. So A dot B plus A dot C is A dot B plus C. They are both the same, right? So we have proved distributive property. A dot B plus C is A dot B plus A dot C. Now I'm going to prove A plus B dot C is A plus B dot A plus C. Okay, A plus B dot C. A plus B dot C dot A plus C. 3 columns, A, B, C. For here, for the left hand side, I need a B dot C. And then I need A plus B dot C. Next, I need for the other side, I need A plus B. I need A plus C. And then I have A plus B dot A plus C. Now for B dot C, you should look for both ones. Here it is both ones. Here they are both ones. All others have some zeros here and there, so 0. Now plus it with the or it with A. So here zeros, first 3 rows. Here there is a 1, 1, and here these are ones. So 1, 1, 1, and here both are 1, 1. Finished. Now A plus B. A plus C. Now dot it. Now look at this column and this column. They are one and the same. So we have proved that A plus B dot C is A plus B dot A plus C. Now special laws. In special laws, we have X plus, okay, we'll keep the same way, not the way we have it in the presentation. A plus A dot B. A plus A dot B equals A. This is the first law. Next is A dot A plus B. Also A. These are the first two special laws. A plus A dot B is A. A plus A dot A plus B is also A. Okay. Now you can apply distributive property for proving this. We can prove by truth table, but since we have learned all the laws of Boolean algebra, it's time to apply them and get the result and prove left hand side is equal to right hand side. So how do I do distributive property? The just previous one, A plus, it is like A plus B dot C, right? It's A plus B dot A plus C. So A plus A dot B is A plus A dot A plus B, right? So let me consider this. A plus A dot B equals A. Now I am saying A plus A is one and A plus B is the other one. Okay, only the left hand side. Now A plus A, we know that A plus A is A, right? A plus A is A dot A plus B. Now I would apply distributive property again, like A dot A plus A dot, just a second, and A dot A plus A dot B. In that A plus A dot B, A will be taken common and 1 plus B. Yeah. Okay, this is A plus A dot B. In this, I shall take it is coming to the original one. I have to take A out and then 1 plus A plus A dot B. So A plus A I took, A dot B I took. Yeah, at this step, A dot A and A plus A in here, A, I will take it here at this step, I'll take A out because in these two terms, in here and in these two terms, A is common. I can write it as 1 plus B. This becomes A plus AB. Here itself, okay. From here itself, I can do that. I don't even have to go by distributing it. See, at this step, what I'm going to do, A plus A dot B I have, right? Now, yeah, this is equal to A dot A plus B, right? A dot A plus B. This is AA plus AB, right? When I multiply AA plus AB. So now in here, this will be equal to AA plus AB is A plus AB, right? A plus AB. In here I have A common. This is A out 1 plus B. 1 plus B is 1 plus like 0 or 1. B could be either 0 or 1. So 1 plus that number like would be 1. So it becomes A dot 1, which is A. In both the terms, I have A common, so I took A out and then I wrote it as 1 plus B, 1 plus B, and 1 plus B, for 1 plus B, I substituted 1 and I have A here. Is that okay? Therefore, I say, I see, I could have done it in the first step. Next recording, yeah, I'm awake. And then I can explain it again. See, in this, like, this is the first, like, you don't even need any more steps from here, from here, because you don't need any more steps from here. I did some, but again, it is coming back to the same original. So you don't even need to do all these. Right from this step, A plus A dot B equals A, because in both of these terms, in it, like this itself can be considered as an expression, and this is an expression. This is the whole expression. Part of this expression is two small expressions. A single variable could also be considered as a Boolean expression. Okay. Now, in here, in this term and in this term, A is common, right? So just left hand side alone, when I can take A out and I can write this as 1 plus B. Okay, so that is what I have done here. A plus AB, I took A out as common and I wrote 1 plus B. Okay, and 1 plus B, if I add anything to 1, the result is going to be a 1. So I just substituted in place of 1 plus B as 1, and A dot 1 is A. Okay. Now, the next is, the next special law is A dot A plus B. A dot A plus B is also equal to A. This is special law 2. Special law 2. Now for this, we can distribute it. A dot A and plus A dot B. A dot A plus A dot B. Now this is A plus A dot B. In this again, is it same like this previous one where we took out A in common and we wrote it as 1 plus B. Now 1 plus B is 1, so A dot 1 equals B. So A dot A plus B is A plus A dot B is also equal to A. Any questions, Henrik? You're okay? Next is A plus, this is special law 3. This is A plus A bar dot B equals A plus B. Okay, this is special law 3. There is special law 4, which is A bar plus A dot B is also equal to is A bar plus B. Okay, so we are coming to that. Now we will solve this. A plus A bar B equals A plus B. In here, distributed A plus A bar dot A plus B. Now what is A plus A bar? 0. Consider A to be 0, 1. 0 plus 1 is 1 and 1 plus 0 is 1. So it is 1 dot A plus B. Multiplicative identity. 1 is multiplicative identity. It is going to end up in the same. A plus B could also be a 0 or 1, right? So this is like, we can say 1 dot A plus B is just A plus B. So this is the left hand side, this is the right hand side, both are one and the same, so we have proved it. Next, special law 4. Special law 4 is A bar plus A dot B equals A bar plus B. A bar plus A dot B. In the previous case, it was A plus A bar B. In here, A bar plus AB. In the previous case, A plus A bar B was A plus B. In here, it is A bar plus B. Okay. So let's expand it, like distribute this addition over multiplication and see what happens. Here, A plus A bar dot A bar plus A dot A bar plus B. So A bar plus A dot A bar plus B. Same idea. A bar plus A is 1 dot A bar plus B. So 1 dot anything is the same. So A bar plus B is going to be the answer. So this is the left hand side, this is the right hand side. Is there any question up to this point? We have seen all the laws of Boolean algebra. We'll be able to solve problem set. I have a question in the chat about problem set 1. Question number 3. Anisha, did you not see the answer key, the answer set, the answers for the problem set?
I saw it, ma'am, but I wasn't able to understand why it was like 4 times 4. So
It's about the bits and bytes, right?
exactly, ma'am.
Oh, okay. Group of 8 bits is a byte. Okay. Those many characters were saying, like using ASCII 7-bit code, we have those many characters to be there in the document. The number of characters in the document was given, and it said how many like in ASCII, if it is represented in number of bytes, what would be the number of symbols required, right, to express those many characters in the document. So we divided by 7 because each symbol is a 7-bit code. So divided by 7 and have it, and you get an answer multiplied by multiply it by 7. Okay, those many characters, so multiply, each character is going to be represented by a 7-bit code, so multiply it by 7 and have those many symbols, and divide it by 8 to get the number of bytes. Finished?
Okay, ma'am.
Okay, anyways, I'll come back to
But
you later.
that wasn't the question. Actually, the question was number 3. You described question number 4.
Okay, fine, we'll come at the end. Okay,
Sure,
now
ma'am. Thank
we are
you.
going through a particular flow, so we will not. Next is De Morgan's laws. All these laws are for what, to simplify the logic expressions. Why do we need to simplify the logic expressions? To minimize the number of gates in the design, circuit design. Okay, De Morgan's laws. De Morgan's laws, like you can easily remember them. Like we did it with the negative gates, I think. Yeah, De Morgan's laws are, you can remember it by break the bar and change the sign. This is a way to remember De Morgan's law. So what does it say? A plus B the whole bar equals A bar dot B bar. A dot B the whole bar equals A bar plus B bar. This is De Morgan's law. A dot B the whole bar. So what did I do in this law? In this law, A plus B the whole bar. What did I do? I just broke this bar and changed the sign. Positive is changed to dot. So when I break the bar goes individually to the variables A bar and B bar. When I change the sign, the plus sign changes to a dot sign. So this is first law. A plus B the whole bar is A bar dot B bar. So when do you get A plus B the whole bar? From which of the logic gates you get the get A plus B the whole bar? You have an OR gate, right? What is the output of an OR gate? An OR gate is A plus B. How about a bubble at the output? NOR gate. So this one gives the output as A plus B the whole bar. So this is same as A bar dot B bar. I have A here, B here. They get complemented and go into a negative AND gate. So it goes as A bar here, it goes as B bar here. And internally it is going to be multiplied, A bar dot B bar. And the output is A bar dot B bar. Now, what could you say about the active high and active low inputs and outputs? This NOR gate is active low output. This negative AND gate is active low input. Though the output produced is the same, A plus B bar, the whole bar is A bar dot B bar, both are one and the same. By truth table we can verify, but still they are functionally different because the complementing, the inversion happens at the output in an OR gate. It happens at the input in the negative AND gate. It's negated and the operation is performed. Here the operation is performed, A plus B is performed, and it is negative. Okay, so that is the difference. Now how to prove using truth table? I'm proving the first law, okay? A here, B here, A plus B, the whole bar. Here A bar dot B bar. If I have 0, 0, 0, 1, 1 0 1 1. If I have for the NOR gate, the output is what? Which is going to have its effect? If I have a 1 in any of the inputs of an NOR gate, the output is going to be forced to a 0, right? It was a 1 in OR gate, now it's a 0, and 0 plus 0 was a 0 for an A plus B output. Now it's going to be a 1. For a negative AND gate, read them opposite. Means what? A complement. 1 dot 1. 1 dot 1 is what? 1. 1 dot 0. 1 dot 0 is 0. 0 dot 1 is a 0. 0 dot 0 is a 0. Why am I reading opposite? Because I have to have the complement of the input variables. So the complements are just the inversion, one-time inversion, one's complement. So 1, I read it as 0, this one I read it as 0, and this one I read it as 0, this 0 I read it as 1, this is 1, 0, 1, 1. Okay. So I have proved by truth table A plus B the whole bar is A bar dot B bar. I have proved. Now I'm going to prove A dot B the whole bar is A bar plus B bar. A dot B the whole bar equals A bar plus B bar. A here, B here. Within this AND gate, it is going to be multiplied. When it comes through the inverter, it is going to be complemented. A dot B the whole bar. Now this is same as A bar complement A, it becomes complement there. B gets complemented by this bubble and send it to an OR gate. Here A bar dot A bar plus B bar, which is the output A bar plus B bar. Now we can prove by truth table A dot B the whole bar and A bar plus B bar 0 0 0 1 1 0 1 1. Now A dot B the whole bar 0 dot 0 used to be a 0. When it is complemented, it's a 1. Now if there is a 0, if there is a 1 in any of the inputs, the output, can you say about it? No, right? If there is a 0 in any of the inputs, 0 dot 1 is 0, but here it is a 1. 1 dot 0 is a 0, here it is a 1. 1 dot 1 is a 1, here it is a 0. So if there is a 0 in any of the inputs, the output is going to be forced to a 1 in the NAND gate. The NAND gate output is going to be a 1 if there is a 0 in any of the inputs. Now A bar plus B bar, I'm going to read A and B opposite and I'm going to add them. So 1 plus 1 is 1, 1 plus 0 is 1, 0 plus 1 is 1, 0 plus 0 is 0. Now they both are matching. A bar plus B bar column and A dot B the whole bar are all the same. So we say that they are the law is proved. Demorgan's law. A dot B the whole bar is A bar plus B bar is proved. Any questions up to this point? What is time? It's going to be 2 o'clock. Do you want to take a break? Let's meet at 2:10. Okay, 15 minutes break. 5:10, 15. Yeah. Now we're going to study about different kinds of Boolean functions. We are going to also make the logic circuits for the Boolean expressions, and we are going to simplify it. Initially, we are going to consider a Boolean expression. We are going to draw the logic circuit for it, and we are going to use the techniques that we have studied, like Boolean algebra and Demorgan's law, simplify the Boolean expression and redraw the circuit and see how much we have saved on the hardware. Okay, how many logic gates went off from the original expression to the final expression. Okay, now the Boolean, we call it as Boolean functions and reduction. We are going to simplify them, simplify the Boolean function. The logic circuit itself could be called as a logic function. Okay, so now I have a Boolean expression y equals a plus b dot bc plus a plus b dot bc plus a. If I have an expression like this, a plus b dot bc plus a. Okay, so how do I have to first sketch a logic circuit or logic function for this. Okay, now let us consider this kind of vertical approach, because it will be very, very clear. I'm taking lines for the inputs. Okay, this is my a, this is my b, this is my c. These A, B, C's could be either 0 or 1s. Okay, now to get A plus B, I take from A, I take from B, and I send through an OR gate, right? A plus B is through an OR gate, so I have the output A plus B here, A plus B here. Now for B dot C, I take from B, I take an input from C, and I send it through an AND gate, and I have here B dot C. Now I have to, for this A plus B dot BC, I have to send again these two outputs through an AND gate. I multiply it here. So I have here A plus B dot BC, right? Now I have to add it with A. So I take from here, from the line A, and since it's addition, I send it through an OR gate. So this is A, and here what I have is Y. Y is now A plus B dot BC plus A. Now I'm going to take the original expression Y and I'm going to simplify it. I'm keeping it for drawing the final simplified circuit. Okay, I'm keeping it ready. And this part is for, this is the original expression. And this part is for the final simplified expression. Let me do it later. First, let us solve this and come back. Now, first one is what? A plus B dot BC plus A, right? Now, what do? I multiply this BC with A plus B with this. Now, I'm applying distributive property. So for this one, multiplying with A, it's A, B, C plus B, B, C. Keep the order of A, B, C, okay? Plus A I have. Now B, when I multiply the same variable 2 times, I get one variable BC, right? So this is ABC plus BC plus A. Now in this, BC is common, right? So I take BC out and it is A plus 1 here plus this A is coming as it is. All right. Now A plus 1, if you add anything to this 1, like through an OR gate, 1 is going to be the result, right? BC dot 1 is the result plus A, right? So BC dot 1 multiplicative identity, it is BC plus A. BC plus A. My expression A plus B dot BC plus A has reduced to BC plus A. Okay, hope you understood. And I'm going back to here to draw the diagram, the logic circuit for the simplified expression, which is BC plus A. So BC is here, A is here, A. This becomes BC plus A. So this is the simplified expression. Now the original expression has required 2 OR gates and 2 AND gates, which could be obtained by just using one AND gate and one OR gate. So this is how simplification helps in reducing the hardware. Is there any question? Now, with respect to order of precedence, when you consider for and OR functions, and always goes first and then OR, okay? First and then OR.
Hello.
Yes. Any question? This is the order and first and OR next. So can you try this one? AB, Y is AB plus A bar C. I have an expression like this. Can you so this order of precedence is for getting sum of product expression, okay? Sum of product means this is sum, these are products, okay? So this is product 1, this is product 2. We are summing the two products, product 1 and product 2. So order of precedence for sum of product expressions is and first and or next. And in this kind of sum of product expression, you do not need the parentheses or the brackets, okay? No parentheses required. When for sum of product, you just do and then next or, no parentheses. No parentheses required. Next. So if you want to implement it, A, B, A bar is also there, C is there here, right? So now A, B, C. Now A dot B. So and goes first in the first level. So it's A dot B and A bar dot C. So for A bar, you could do this, A bar dot C. A bar dot C, or them both. This is now AB plus A bar C. No, we cannot simplify further than this, because if you take out, like if you multiply A plus A bar dot is we can try it, okay, just for fun, okay. This is the simplest expression. This is the minimum possible, because here if you go further, you can multiply this and this and this and this and try. That is the only possible thing, right? So A plus A bar, next is A plus C, next is A bar plus B, A bar plus B, and B plus C. Okay, now A plus A bar is 1, right? 1 dot A plus C and A bar plus B, then B plus C. In here, in these two, if you take C out, right, C out as common, you can have okay, after that you have to again multiply them and get the product terms, okay. It just keeps going on and on. See here, this and this and this. Next it becomes A bar plus AB plus A bar C plus BC for this part, and then it will go with B plus C. So you see it is getting, okay. See, A plus A bar, when you have, it is going to be 0, and then it is going to be AB plus A bar C plus BC with B plus C, and again you multiply them, AB plus A bar C plus BC times B plus C. So B plus C dot AB, B plus C dot A bar C plus B plus C dot BC, and or you can even do this. And then with this. It's not simplifying, right? It's expanding. So for the sum of product, it is ending in a sum of product at this point with the least number of variables. That is the end of it. Next is product of sum. The expression is going to look like A plus B, A plus B bar plus C, one sample expression I'm taking. And in here, what you do, this is a dot, right? Now, what you do first is to or first, and next. If you don't have these parentheses, it would become very, very complicated, right? Like if you write it also, you will see how complicated it looks. A plus B dot A plus B bar plus C. If you write, you wouldn't know if you have to multiply these two as AB and then A plus AB plus B bar plus C, right? So therefore, it's always required to have parentheses in the product of some expression. So parentheses are required. Not required. This is very important in product of some expressions. Now, if I have to implement this, A plus B plus A bar plus B, A plus B bar plus C, I would go for again this format, A, B, and C. And A plus B is here, A plus B through a OR gate. Next is A plus B bar plus C. Again, they have to go through an OR gate. Level 1 is OR gate. Here, A plus B bar plus C, and these two to be sent to a AND gate. Here we have A plus B dot A plus B bar plus C. So if you have an expression like y equals A B bar plus C, if you have something like this, how would you do? Again, do by this A, B, C. A dot B bar, AND gate, A, B bar, and with C, it has to be added. This is Y equals A, B bar plus C. This bubble is nothing but a NOT gate. It's a NOT gate. Okay. So if I give here, if I send C here, once again, A plus B bar is to be from here. This is B line, I take from here, this becomes B bar by the inverter. If I send C here, it becomes C bar. If I send B here, it becomes B bar. And C is here. It is going to the second OR gate. Now, if you want to find the value of this, if you want to find the value, like it can only be a 0 or 1, right? So we need to go for a truth table, okay? To get, if I ask you to get the truth table output of this y equals a b bar plus c, what you need to do is you need to make a truth table with 8 combinations because there are 3 inputs, right? So A, B, C. Next next is the final, like you have A, B bar, so have A, B bar, A, B, C. If you want, you can have one row for C, one column for C bar, or B bar, for in this case B bar, so that you won't make any mistakes. and here y. Okay, so the 8 combinations possible are 0, 0, 0 to 1, 1, 1. Okay, now a b bar, I have to read b opposite. Okay, 0.1 0, 0.1 0, 0.0 0, 0.0 0 again, 0 1.1, right, opposite, 1.1 1.1 1.0 1.0. Next output y, it has to be added, ab bar plus c, right, ab bar plus c, this is 0, this is 1, this is 0, this is 1, this is 1, this is 1, this is 0, this is 1. So if you connect here a positive logic, like maybe like this, if you connect an LED, and connect it to ground, what happens is this LED is going to glow for these combinations A, B, 0, 0 and C alone 1. If this switch is like closed, you're going to have a 1, the LED is going to glow. So when these two switches are closed, the LED is going to glow. Then first switch alone closed, LED glow. First and C, A and C closed, LED will glow. And all the switches closed, then again the LED will glow. So this is the truth table output. Now this is logic circuit. What is this? Logic expression. This is logic circuit. Implementing the logic function, this is also called a logic circuit or logic function. We are implementing the logic expression. We are getting the truth table results. And by doing the connection of an LED, you will be able to see the glow of the LED for 1 outputs. Any questions? Now, I should give you an expression. You draw the logic function or the logic circuit, and then you try to reduce the logic expression and get me the output. Now, the given logic function, the logic expression is y equals a bar b bar c plus a bar c bar plus b. Now, what am I asking you? Sketch the logic function, simplify logic expression using Boolean Algebra and sketch the logic circuit or function of the simplified logic expression. Try it. First is to draw, okay? First is to draw the circuit. Then using Boolean algebra rules, we are going to reduce or simplify. Then we are going to draw the logic function for the reduced logic expression. Hope you're all doing it. In here, the logic expression is given. You're getting the logic circuit, right? You're getting the logic function, and then you're drawing the logic function, and then you're reducing it, right? So in here, let me help you. A, B, and C. So A bar, B bar, C. This one. Where are they going? They're going to an AND gate. It is A bar, B bar, C. Next, this is A bar, C bar. So here A, B, C. A bar and C bar. A bar and C bar. A, B bar, C, and here A bar, C bar. Plus B. So first product, second product, this is a variable. All must be added. Here you have Y. So we have implemented the logic function, right? We have implemented the logic function. Now we are going to reduce this logic expression. In these two, A bar is common, right? Instead we cannot say. Now you have you take your time to reduce it the way you want. Come with the result. I want to check how you are able to reduce it. This is like A bar plus AB form. If you consider this, this is like this is A, okay, B. If this is A, this is A bar, right? So A bar plus AB form. What is A bar plus AB according to the special laws? A bar plus AB. Do we have any special laws? A bar plus AB. Here. Special law 4. A bar plus AB. A bar plus AB is what? A bar plus B, right? A bar plus AB is A bar plus B. A bar plus AB is A bar plus B, right? So it is C bar plus B bar. A is going off. A bar plus B, this is A bar plus B. In the place of A bar, we have C bar. In the place of B, we have B bar. We have B bar. So the answer is C bar plus B bar. So A bar is here, B bar plus C bar plus B.
Ma'am, can you please repeat it one more time after the second line?
Yes. Here, A bar is like I have taken in these two terms, I have taken A bar out. So I have B bar C plus C bar only in here. All right. Now this part alone is like the special law A bar plus AB format. C bar plus B bar, CB bar. In the place of A bar, I have C bar. In the place of B, I have B bar, right? Now, therefore, I can write A bar plus B, right? A bar is what? C bar. So, I've written C bar. Okay. A bar is C bar here. B is B bar here. A bar plus B. So, it is B bar plus C. And this A bar as it is, this B as it is. Now, I'm going to consider these two. A bar B, B plus A bar B bar, okay? Or I can write it like this, B plus B bar A bar plus A bar C, okay? This is in the form A plus A bar B. This is in the place of A, I have this, in the place of A bar, I have B bar. This is B, my B. A plus A bar B. Look in the special laws, A plus A bar B. A plus A bar B is what? A plus B. Alright, A plus A bar B formula is saying it is A plus B. So try to apply it here. A plus A bar B formula is what? A plus B, right? So what is A? A is B. And what is B? B is A bar. So the answer is A plus B, right? So I would write B plus A bar. That's it for this. B plus B bar A is B plus A bar by the formula, A plus A bar B formula. A plus A bar B is what? Equals A plus B is the answer. So in the place of A, I have B. In the place of B, I have A bar. I have written it. Plus this is as it is. A bar C comes up. Now I shall consider these two, A bar plus A bar C. Okay, I shall take B here and I'll take A bar out 1 plus C. 1 plus C. Right? A bar is like 1 times A bar and C is multiplied and we C A bar. Now 1 plus C is what? It's 1, right? A bar dot 1 plus B. It is B plus A bar. B plus A bar. A bar dot 1 is A bar. So that is it. So the final is y equals B plus A bar. Now the original expression has required 1, 2, 3, 4 NOT gates, 2 AND gates, and a 3 input OR gate. Now the final expression is just B plus A bar. The final expression, final simplified expression is y equals B plus A bar. It is good to write A first, A bar plus B, okay? Or leave it like that. So you need just a NOT gate for A to make it A bar. You have B and you send it through an OR gate. and this is y. See, these many gates have reduced to just one gate like this by Boolean algebra. Thanks, Sandeep. You're helping in my chat once again. Now, next thing is, if you have a truth table, okay, how to bring this expression we are going to see. Okay, how to bring the expression from a truth table. Y equals, okay, I don't know. First, I have a table, truth table, ABC and output Y. Now, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. If I have something like 1 here, I have maybe 1 here, I have a 1 here, and all other places I have zeros. Okay. If I have to bring the logic expression for this truth table, logic expression from truth table. What do? I get the product terms of this. Like what I do is, like this is called getting the min terms, okay? Wherever I have a 1, and those are going to be the product terms of the sum of product expression, and I just add these. So 1 is when A is 0, B is 0, and C is 1. Okay. Whenever there is a 0, I take the complemented form of that variable. Okay. Against this one, I have 0, 0, 1. This 0 is A bar because it belongs to the A column, right? And this B is 0, then it is B bar. And this is uncomplemented, so I write C as it is. Now I'm getting the logic expression. Plus, this is one min term. I call it as min term. This product term is called min term. Next is, here I have 1 here. So A is what? 0. So if A is 0, I write it as A bar. B is 1, so B is uncomplemented. C is 1, C is also uncomplemented. Now for this plus, and this is what? A, B, C bar. Okay, A, B, C bar. Now my Y equals A bar B bar C plus A bar B C plus A B C bar. So this is my logic expression. Now I can draw the logic function for this, and I can reduce the expression using Boolean algebra, and I can get the simplified expression, and I can see how many gates I would need. So each of the product term, this is okay, this is a product term, this is a product term. So product 1, product 2, product 3. These are called min terms. Min term 1, min term 2, min term 3. the whole of it is called a sum of product expression. Whole of it together, we call it as sum of product expression. Okay. Now you see, you have an XOR function, okay? XOR function. Let us get the min terms of XOR function, okay? Here you have A, B, A XOR B, 0, 0, 0, 1, 1, 0, 1, 1. So A XOR B is 0 as long as the inputs are the same, 1 otherwise. Whenever there is a difference in input, the output is going to be a 1 in XOR. Now XOR function A, B, I just wrote the combinations for A and B. A XOR B is 0 if the inputs are the same, 1 if there is a change in input. Now if you want to write the min terms for this A XOR B, now A XOR B equals what? That is your Y, right? A XOR B. 1 when A in the complemented form, which is A bar, and B, A bar B, plus this is what A in its uncomplemented form, A. And how is B? B is in the complemented form. So A bar B plus A B bar. So these are the min terms of XOR function. This is again a sum of product expression. Now, can you sketch the logic circuit or the logic function for this XOR gate? What would you do? You take the inputs. You're going to implement it, finished, okay? A and B, two inputs, A, B. You need A bar, B. Send it through AND gate. Next is A, B bar. A and B bar. Send it through another AND gate. They both should be odd. So send it through an OR gate. This is your A XOR B. We can get the complement function of the original function, okay? So for example, if I say this is y equals A XOR B equals this, I can get the complement function by changing the zeros to ones and ones to zeros, okay? So the complement function is obtained by changing the zeros to ones and ones to zeros, okay? So it is A XOR B complement, okay? Y bar is A XOR B complement. So what do? I have to just change the ones to zeros and zeros to ones by inverting A bar B plus A B bar, the whole bar, okay? Now if you apply Demorgan's law to it, break the bar and change the sign. So it is going to become A bar B bar dot A B bar, the whole bar. It will become like this, right? Now if you apply same Demorgan's law, break the bar and change the sign, it's becoming A double bar plus B bar, right? Dot A bar plus B double bar. It will become like this. Now what you do, double bars, whenever you invert number 2 times, it is going to end up in the original number, right? So this becomes A plus B bar dot A bar plus B. Now you can simplify using you can simplify using Boolean algebra. How do you do that? You have to multiply, right? And then again the same with the other variable on this side. Yeah, we're going to do this. Now A dot A bar plus A bar B bar plus AB plus BB bar, right? Let me write it here. A dot A bar, A bar plus A bar B, A bar B plus B bar B, B bar A bar, A bar B bar, okay, A bar, A bar, AB, right? AB, A bar plus AB plus A bar B bar plus B bar, right? Now this one B bar and A bar would get cancelled because you somehow have a 0 in the multiplication, A bar and B bar. So what is it ending up in? AB plus A bar B bar. So where is AB? AB is here in the truth table. AB is here and A bar B bar is here, right? Therefore, they are going to have 1 and 0 otherwise. So zeros should be changed to ones and ones should be changed to zeros to get the complement of the original function, complementing function. So if you want to sketch the truth table for y bar equals a like a XOR b the whole complement. So a XOR b complement 0 0 0 1 1 0 1 1. Zeros from here should be changed to ones and ones should be changed to zeros. That's it. Now from here we can write again we have to take the ones to write the min terms. So the min terms are a bar b bar plus ab. All right, this is what we obtained here also, ab plus a bar b bar. So this is what is called complement function. Complement function. Is that okay? We have something called product of sum form. Have you noted it? We'll go for product of sum. Product of sum expressions, or with sum of product expressions we get min terms. With sum of product expressions we get min terms. With product of sum we get max terms. Okay, so these are odd terms. The max terms are odd terms. From this we get max terms, which are odd terms. In here, in sum of product expression, what we get is min term. Min terms are product terms. But with the product of sum expressions, we get max terms. So how the expressions would be? It would be like a plus b plus C plus D dot A bar plus B bar plus C plus D bar. This is all, each of them, if y equals this, if y equals this is a max term 1, this is max term 2. What are these terms? These are odd terms. Odd term 1, odd term 2. Now, if we have to get the sum of product expression from a product of some expression, we can apply Demorgan's law. We'll find the, I'll show you. For example, you have a truth table like this. The combinations you have like this, and you have y. This is going to have some ones here and there randomly. You have a 1 here, you have a 1 here, you have zeros here. Now, if you want to find the output, y equals, you collect these ones and then write them. Write the min terms first. So you get the sum of product expression first, okay? A bar, B bar, C bar, okay? Plus, you have here A bar, B, C, plus A, B bar, C bar, right? Now to get the product, this is sum of product expression. Now to get the product of some expression, you should complement it. That's why we studied about the complement. This is sum of product expression. Y equals A bar B bar C bar plus A bar B C plus A B bar C bar. From where did I get? I collected these ones, and for the zero, wherever I see 0 for a variable, I took the complemented form of that variable, and for ones I took the uncomplemented. So this is A bar B bar C bar. Next is, this is A bar B C. This is A B bar C bar. I noted it here, and Y bar is equal to A bar B bar C bar plus A bar B C plus A B bar C bar, the whole bar, where we apply the De law to get the product of some expression. Okay, now here A bar B bar, yeah, this is one way of doing it. And you could also take the 0 terms, okay? Take the 0 terms and write the sum of product expression and complement it for getting the product of sum, okay? So here, 5 of them. So here you see, this is sum of product, see here. This is A bar, B bar, C, right? So this is A bar, B bar C. This is A bar B C bar. A bar B C bar. And this one is A B bar C. A B bar C. This is A B C bar. And this is A B C. A B C. Now you write this. Y bar equals A bar B bar C plus A bar B C bar plus AB. I'm sorry. Okay, I'm going to explain again this one here. The product of some expression could be obtained from sum of product expressions. How do you get it? Sum of product expression, we have to get the complement of the sum of product expression. So y bar you should write. For getting y bar, you consider the zero terms and get the product terms, okay, the min terms for zeros. So here I have 0, 0, 5 places. So these are the 5 min terms, okay. So here, this is A bar B bar C, A bar B C bar, A B bar C, A B C bar, A B C. All are zero, so Y complement is this. And after that, what you do? You're going to complement it and you're going to apply Demorgan's law. When you complement it, you have bars already here, A bar B bar C. So A bar becomes A double bar plus B double bar plus C. So double bars will get cancelled and you have this term, which is a max term, which is a sum term. So the same idea for all of these terms, apply Demorgan's law and get them. After getting them, you're going to send for each of this term, you're going to use OR gates, and to multiply all the terms, you're using AND gate. There ends the chapter.